So I am excited to get a chance to kick things off here, and my assignment is to give you an observational view of the interstellar medium in nearby galaxies. So I'm going to go through things in roughly this order, and let me sort of give you my kind of how I interpreted the directive to talk about the interstellar medium of nearby galaxies. So especially since this is the first of the lectures, I'm going to start us off and take between the first third and half to talk about the different phases of the interstellar medium in low redshift galaxies and just give a sketch of how we observe them. It seems like this is sort of important to kind of lay out the basics and terminology at the beginning of the first day. I'm then going to split the rest of the lecture between discussing the content of the interstellar medium in low redshift galaxies and giving a overview of the structure of the gas. So I'll say a few words about star formation, but I'm mostly going to focus on the sort of content and basic shape of the interstellar medium in nearby galaxies. Because of essentially we're doing this in 1.5 hours to cover the interstellar medium of all the galaxies in the nearby universe, and as Frederick really nicely pointed out, we have a wide range of backgrounds. I'm going to try to keep things high level, by which I mean accessible to as many of the participants as possible. And of course, we have to be brief. So that means that I'm going to simplify, I'm going to go fast in a couple of places. I'll leave an incomplete bibliography at the end of the talk, and absolutely encourage you to follow up with questions and via the pinned link in Slack or here in the Zoom channel. You should have access to the slides if you want to follow along. So I think the last bit of preamble is just to point out that I expect and hope that the lecture here will overlap and hopefully duplicate a little bit quite a few of the other lectures. Of course, many of the ways that we learn about how the interstellar medium is changing over cosmic time is to contrast the interstellar medium at low and high redshift. The phases, although they change in their balance and character, do sort of persist across galaxies so I'm going to show pictures of the Milky Way, and these are the same phases that are present at high redshift. And then, of course, the big thing here, which is a motivating factor for the school, is that when we attempt to put together a complete picture of the interstellar medium, what we're often trying to do is combining details from studies of the Milky Way or the absolute nearest galaxies with the sort of big picture that you get from surveying galaxies, and especially from surveying galaxies across cosmic time. And then finally, I'm going to talk a bunch about observations. I'm going to be very observationally anchored. But of course, increasingly, the interpretation of these observations, because the ISM is this complex system that combines a bunch of different physical conditions and different species, the interpretation of observations relies on detailed physical knowledge or detailed physical models that are leveraging the sort of rich spectral and multi-wavelength information that I'll talk about here. And we're really lucky that we have an outstanding set of lectures running through the rest of the school on how observations can be interpreted physically. So with all that said, the sort of thing that you're looking at here is that my goal here is to introduce the ISM phases, tell you about the basic observational approaches, give you the terminology that's going to be used through the rest of the school, and then give you a basic sketch of what's in the interstellar medium of galaxies at redshift essentially 0. We'll talk a little bit about mergers, but everything is kind of at a redshift of less than a few hundredths here. So with that preamble said, let's go ahead and dive in. So I'm going to start by just stepping through the interstellar medium phases here. And at low redshift, this needs to start with atomic gas. So atomic gas, which you'll hear shorthanded as H1, is the dominant phase of the interstellar medium in the disks of galaxies at redshift 0. So in this phase, the hydrogen is neutral with a proton and electron together. This gas isn't sitting at a particular density and temperature. Instead, it has a wide range of temperatures and densities. And at least in the solar neighborhood, is often conceived of as having a roughly fixed thermal pressure of 3,000, 3,500, something like that, P over K, which means that the density and the temperature should multiply to give you about 3,000. So in the classical view, there are two stable equilibria based on the heating and cooling curves, and those produce a cold neutral medium, which is a phase of the atomic gas at something like 100 Kelvin with densities of a few tens of particles per cubic centimeter. This is not volume filling. It's denser and more compact than the warm neutral medium phase, but has of order the same amount of mass in it. And then there's a much more volume filling warm neutral medium, which has temperature more like 5,000 degrees Kelvin. And that implies a density that's much lower. You could do worse than just walking around thinking about the diffuse H1 as having 1 particle per cc. But you can say maybe something like 0.6 particles per cubic centimeter. This phase is more nearly volume filling something like 40 or 50% of the gas in the disk of a galaxy like the Milky Way, with most of the balance filled by hot gas, although warm gas, as you move away from the plane, plays an increasingly large role. The modern view of atomic gas is that unstable gas is also present, meaning that the systems that we actually look at when we actually look at a real galaxy are more dynamic, and you will catch gas moving between these warm and cool phases. So that if somebody stops you on the street and asks you how much is in each of these phases, you could say a third, a third, a third, and not be giving an absolutely terrible answer. How do we see this atomic gas? For almost for more than half a century now, the answer to this has been that we observe the atomic gas using the 21 centimeter line. It's not the only way to see atomic gas. I'll talk about that. I'll show another slide on this in just a sec. But the workhorse tracer of tracing atomic gas in galaxies has been the H1 21 centimeter line. So this is the hyperfine transition. It's a spin flip, and it's extremely unlikely for an individual H1 atom. The Einstein A implies a decay time of something like 10 million years. Fortunately, there's a lot of hydrogen. So the idea here is that hydrogen in interstellar space will naturally excite itself to have level populations that are roughly tracking the degeneracies of the states. I'm not going to get into the idea of spin temperature here, although I suspect that'll come up in later lectures. And the point here would be that the spontaneous decay of these things produces a line at 21 centimeters, which is 1.4 gigahertz. And that modulo optical depth concerns, this line has such a low critical density that it's easily excited and directly traces the mass and kinematics of atomic gas. Tracing most of the gas that fills the space of galaxies turns out to be very important. So this is a main part of the mission of quite a few radio telescopes, including the sort of grand old very large array, and the WSRT, but also including new telescopes like FAST and MEERKAT, and the Green Bank Observatory. So all of these things have observing the 21 centimeter line to trace the atomic phase of the interstellar medium as a core part of their mission, in addition to ASCAP and GMRT, and almost all parts of the map that we saw covered have working 21 centimeter telescopes. This is just to show you what it looks like when you take a picture of the 21 centimeter line emission from galaxies. I'll come back to this a little bit. These are maps made with Westerberg and with the Very Large Array. And the idea here is that as long as you can assume that the gas that you're looking at is optically thin, which is mostly okay, but not 100% right, and is certainly something that you would worry more about as a galaxy becomes more edge on or more zoomed in like the Milky Way. And as long as the density is above the critical density of H1, which is a totally safe assumption, what you're looking at here is can be translated directly from the intensity of the 21 centimeter line into a view of the mass of atomic gas. So these are really maps of the atomic interstellar medium to first order. And to second order, there's a lot of interesting things to say. But so these aren't the only ways to trace atomic gas. There are older ways to trace atomic gas, including looking at optical absorption lines of quite a few species of metals in the optical and ultraviolet, but also emission from, for example, the C+ line. The 158 micron C+ line is the sort of dominant coolant over a big part of the interstellar medium, including the atomic phase. And observations of this line can trace especially the cold neutral medium of the atomic gas. Similarly, there is dust mixed through the entire interstellar medium with a varying abundance. We're going to hear a lot more about later in both this lecture and this week. So these other tracers of the interstellar medium are crucial and have been crucial for various applications. One of the caveats here, of course, is that there is also dust mixed with molecular gas and ionized gas, and the C+, as I'll mention again in a couple of slides, suffers from the same potential ambiguity. So that, there's a reason we keep coming back to 21 centimeter, but there are also very important reasons that you would use these other potential tracers of the atomic medium. So I'm mostly going to mention these, but then mostly show you results from 21 centimeter when we get to the content of, when we get to the interstellar medium content of local galaxies. So from the sort of mass-bearing, volume-filling phase of the H1, we can zoom in to the denser and colder molecular gas that we understand to essentially host all star formation. So this is the phase of the interstellar medium that's most directly associated with star formation in both the Milky Way and other galaxies. I'll come back to this at the very end of the lecture. So in the Milky Way, there is some uncertainty about the overall mass of the molecular medium, as there is everywhere, but roughly you could think about something like 20% of the overall interstellar medium in the disk of the galaxy sitting in the molecular phase. This is very much not a smooth spread out component, but the molecular gas is clumped up into marginally bound, and we'll look at what that means further into the lecture, highly turbulent clouds that have a high degree of structure, and we'll hear a lot more about that in the lectures on the Milky Way, I'm sure. So these things have a very wide range of densities. I think keeping a number like 100 up to 10 to the 5th particles per cc in mind is reasonable, but doesn't do justice to the densest parts of the molecular clouds, where the actual stars have begun to form. These things have sizes, the clouds that hold the molecular gas have sizes of something like 10 to 100 parsecs. And their structures are clumpy and filamentary. And you can see that here in pictures of a couple of the nearest clouds to us. This is the Taurus molecular cloud, and one of, I think, the prettiest pictures ever taken by a single dish telescope. And this is the Orion cloud complex, which is the nearest high mass star forming region to our home here in the Milky Way, or in the solar neighborhood. So the molecular phase of the ISM has a problem, which is that it is extremely difficult to see. So the fundamental issue here is stated in a few different ways, but is basically that at the densities and temperatures found in most molecular clouds, the dominant component by mass, which is H2 itself, is practically invisible. And so as a result, when people go observe the molecular gas in galaxies or in our own galaxy, they almost always end up resorting to a proxy of some type, the exception being absorption measurements, which have their own host of potential issues. So the most tracers of molecular gas in other galaxies are emission from a wide variety of molecules, although I think we will hear a bunch of really neat results also using the C+ line as we move through this school. So at low redshift, CO emission ends up being the workhorse tracer. I'll talk about this in the next slide. But dust emission also plays a very prominent role. In the Milky Way and in a few other places, you can use potentially very powerful, but also harder to deploy techniques like gamma rays or UV absorption. And then increasingly, C1 and C+ emission can also be extremely useful to trace out the location of molecular gas. So the important thing that you want to keep in mind here is that all of these tracers are fundamentally proxies. They're indirect. They are tracing things that are mixed with the molecular gas, and they come with important caveats. And we do not have a tracer that satisfies all three of these criteria perfectly. But as you think about ways to trace H2, it's worth thinking about, is your tracer ambiguous? Meaning, is it also tracing the H1 and the ionized gas? Is it straightforward to convert directly between your observations and the mass? Meaning of molecular gas, meaning is it a stable proxy? And then if you come up with the perfect tracer, but you can't detect it, then the ability to deploy something like this in survey mode would be limited. So this is just sketching something that you will see much, much more nicely later in the school, I am sure. The sketch of imagining looking into a molecular cloud. So here you sit outside a molecular cloud in a region of ionized gas, and you look in through the surface of a molecular cloud. This is just illustrating some of the issues with some of these tracers. So as you go from ionized gas to neutral gas to molecular gas, the phase that the carbon sits in shifts. And we are interested in these species because they produce very bright lines and because they are comparatively the next most abundant species to H2. You can see that the C+ here nicely illuminates the outer parts of the molecular cloud. C1 is an interesting case, may never actually become the dominant reservoir of carbon, but it's likely to emerge probably exclusively from within the molecular cloud. And then as you go deep into a molecular cloud, not so deep, maybe up to at a shielding magnitude of something like a magnitude, you'll see the carbon convert to mostly CO. And throughout this whole thing, dust is mixed with this. So you could imagine that in various ways, observing C+, observing C1, observing CO, or observing dust, with some caveats, would give you a chance to get at this H2, which is the actual mass of sort of dense cold stuff that you think is directly involved in star formation. So at low redshift, there are a lot of other options, but the truth is that we still lean quite heavily on CO emission. And there's a reason for that. So as a tracer for molecular gas, CO is nice because it's the second most abundant molecule, and because it's the primary reservoir of gas phase carbon deep inside the cloud, so above a sort of extinction of about a magnitude. Because the emission from the CO molecules are easily excited with relatively low effective critical densities. These lines, so the low J, so these are rotational transitions, lines of carbon monoxide in the millimeter part of the spectrum, light up pretty easily and give us a pretty good tracer of the distribution of mass and kinematics of molecular gas. This is a useful enough tracer that we've been doing this for almost 50 years at this point. But there sort of remains the the technical but frequently highly relevant issue to a ton of what I'll talk about, that the translation between the brightness of CO, or the luminosity of CO, and mass, which is referred to as XCO or alpha CO, we don't know nothing about this. We have some pretty good numbers. We have a good handle on what this number is in the Milky Way with some attached uncertainty. But this is still a topic of active research that is a fundamental is a fundamental limitation to our knowledge of the amount and distribution of molecular gas in galaxies. So I've included a few notes here just defining the CO to H2 conversion factor. This is just a mass to light ratio, meaning that this is just expressing the conversion between luminosity often expressed in these terrible units of CO emission and the mass of molecular gas that you expect to be associated with that. This is a CO1 to 0 conversion factor. This can also be expressed in XCO units. So these two are the Milky Way values that are equivalent to one another modulo some unit changes in accounting for helium. The crucial thing for talking about conversion factors in nearby galaxies is that we know that this CO to H2 conversion factor depends on metallicity. So it's higher in low mass, low metallicity galaxies. And we know that it depends on excitation and optical depth. So with the sense that it's lower and diffuse, optically thin, and hot excited gas. So CO, so hopefully that gives you a bit of an introduction to CO, which is our main sort of workhorse tracer of molecular gas at low redshift. So carbon monoxide's rotational lines are the brightest, but hardly the only molecular lines that we have access to. There's a whole host of other molecules mixed with H2. And you can observe these molecular lines via spectroscopy running all the way from the radio up to the infrared part of the spectrum. The key thing here is that the individual lines that we see have different sensitivities to temperature, density, and chemistry. And so that means that similar to what you get out of optical spectroscopy, by contrasting the brightnesses of different molecular lines, you can get a handle on physical conditions, abundances of different species, excitation, density, these kinds of things. So as a practical matter, these lines that are not rotational transitions of CO, except in very dense, very well excited, very optically thick systems, these lines are almost always fainter than CO. But together, they provide a really nice toolbox that can be used to explore the physical conditions and chemistry of the molecular interstellar medium. And I'm illustrating here just a part of the spectrum of a local starburst galaxy. I'm really hopeful that by the time people are showing this next year, that the Alchemy large program on ALMA should be giving us just an absolutely beautiful view of all the lines that are present in local starburst galaxies. I had highlighted the kinds of telescopes that do 21 centimeters. So the radio telescopes observing observing 1 to 2 gigahertz emission. To observe CO emission, the interferometer is actively doing this right now, and I'm sure I have forgotten one, but would be ALMA, NOEMA, and the submillimeter array. So these are powerful arrays to image molecular line emission from galaxies at high angular resolution and give us maps of molecular gas structure, kinematics, and physical conditions as they probe different lines. But if what we want to do is to either map the nearest galaxies or just map out the molecular content of galaxies, single dish telescopes like the IRM 30 meter, the LMT, JCMT, APEX, the NOBI-ALMA telescope, and even Green Bank at these frequencies end up being fantastic tools to capture the integrated emission from galaxies. So if you wanted to instead trace the molecular gas using dust, submillimeter observations are currently possible with ALMA, the submillimeter array, or bolometer arrays on an overlapping set of single dish telescopes. Unfortunately, right now, our only access to the sort of peak of the dust infrared spectral energy distribution is coming from SOFIA, but there's an amazing archival researches or their amazing archival data thanks to really fantastic missions like Herschel, WISE, Spitzer, IRAS, and so on, and Planck. So that's an introduction to the dense cold phase, the molecular phase of the interstellar medium. Let's now say you've taken your atomic gas, you've formed it into a dense cloud, and it's formed stars. Those stars will play an important role in creating a warm ionized medium. So there's also warm ionized gas. So to first order, in a normal star-forming galaxy like the Milky Way, this is not exclusively where this gas comes from, this warm ionized gas surrounds massive young stars as H2 regions. And then because those H2 regions only account for something like half of the ionizing photons coming out of the young massive stars, a medium of warm ionized gas also pervades galaxies. And this is either referred to as diffuse ionized gas or the warm ionized medium, depending on whether you are a Milky Way researcher or the other way around, but an extragalactic researcher or a Milky Way researcher. So this warm ionized gas ends up being incredibly important in studies of how galaxies form and evolve, because not only do the H2 regions serve as signposts that massive star formation is happening, but as we'll see in just a second, the warm ionized medium offers us diagnostics, especially to the abundance of heavy elements, but to the physical conditions and the power sources that are present in the galaxy. In terms of this sort of diffuse ionized gas, our tracers of this tend to be sensitive to the density of the gas, and so actually getting a perfect accounting of the overall mass of the warm ionized medium gets tricky for a couple of reasons. But it's not crazy to think about saying that this diffuse ionized gas or warm ionized medium might account for as much as 20 or 30% of the mass in the disk of a galaxy like the Milky Way, with a more extended vertical distribution than some of the colder phases. The warm ionized gas may not be dominant by mass, but as I just mentioned, this ends up being an incredibly powerful tool to diagnose all sorts of things about a galaxy. So the recombination line emission from H2 regions, which include H alpha, but also H beta, the Paschen series and bracket series in the infrared, all the way down to radio recombination lines observable with ALMA or even with the VLA, can trace the ionizing photon production of the stellar population. That's a way to trace the number of high mass young stars, and via that, the star formation rate. If you start to get recombination lines from helium, you have information on the shape of the radiation field. Because the temperature of H2 regions depends on metal content via the influence of metals on cooling, gauging temperature or gauging the physical state of H2 regions ends up being, and this is really crucial to understanding galaxy evolution, a main probe of metallicity. So beyond this, ratios among the electronic transitions, especially closely spaced electronic transitions of different atoms and ions, are very powerful as a way to reveal the relative influence of shocks in star formation and AGN activity. I think we'll hear a lot more about these various BPT diagrams as we move forward in the week. This is just an illustration of how rich the spectrum, this is just the optical spectrum of an H2 region from a nearby galaxy. This is a spectrum from NGC 628 from a paper using the LBT as part of the chaos survey. So to say a word about observing ionized gas, so observations, you might think we've been doing optical observations forever and nothing is new, but nothing in fact could be further from the truth. So our observations of optical spectroscopy of galaxies and especially nearby galaxies have just absolutely exploded over the last 15 years and over the last 10 years in particular. And Nicola showed us a nice illustration of this from Muse in the introductory slides. But the big advance here has been the widespread deployment of these integral field units. So, now for the first time in, ever, I guess, there are a host of instruments that can make a map of the spectra point by point across a nearby galaxy, covering either the full or partial optical spectrum of part of that region. We'll get similar capabilities moving into the near infrared. We have some already from ground-based telescopes, but from JWST over a narrow field. So leveraging this, really Khalifa and the Sauron and Atlas 3D surveys were amazing pathfinders for this. And then leveraging this, the big Manga and SAMI surveys have essentially gone out and just gotten optical spectral maps of hundreds and thousands of galaxies. And then in order to make maps in more detail, the MUSE instrument on the VLT has just been absolutely amazing. So the Keck KCWI is also coming into its own. But I think this MUSE facility on the VLT is, you can see a picture of the instrument itself here. It's just absolutely stunning to have this sort of optical spectrum by optical spectrum capabilities on the back of an 8-meter telescope. This is all I'm going to say totally unfairly about the hot ionized gas. I hope we'll hear more of it in the lectures on the Milky Way itself. You know, I said that the warm neutral medium was partially volume filling at a sort of 40 or 50% level. The rest of the space in the interstellar medium is filled by a mixture of the warm ionized medium, and then a lot of the volume gets filled by essentially hot million Kelvin gas. So you can think about this as filling sort of about half the volume of the interstellar medium. So this is gas that's heated up to near 1 million Kelvin by supernova shocks. It fills an enormous volume, but because it's in approximate pressure equilibrium with the surrounding material, you can imagine that having those very high temperatures implies very, very low densities, and it constitutes only a very minor fraction of the overall mass of the total ISM. So these supernova shocks are really crucial. We'll have a whole lecture on shocks, and their effect on topology is essential. But in terms of an overall mass budget, the hot gas does not contribute overwhelmingly. This gas is highly observable, and I want to say a word about this picture in just a sec. And in particular, it's observable via X-ray emission and via absorption studies in both the X-ray and the ultraviolet. But this is not easy, and we haven't, you know, although the diffuse X-ray emission has absolutely been detected in other galaxies, including some beautiful studies at the LMC. This is difficult to survey across the entire galaxy population. So this has been perhaps a little less well studied across the entire low redshift galaxy population. So, you know, what I will say is that if this is something that's interesting, go back 2 or 3 weeks, I can't remember the exact date, on arXiv and see the enormous crop of extremely interesting papers from the new Rosita telescope, which just came out, and among other things, you know, is producing this picture of our local view of the Milky Way. And you can see just a stunning amount of diffuse gas filling the Milky Way. And then this central feature, although not always agreed to be this, is now, I believe, understood to be the signpost of the wind being launched from the center of the Milky Way, analogous to the Fermi bubble. And this is the biggest, you know, this inventory is the biggest part of the talk. So just to say, so bear along with me here, we'll pause just a sec to see if there are burning questions in a few slides. But so that takes us through our sort of stepping through the different things that hydrogen can be doing. But of course, we know that hydrogen isn't the end of the story. So by mass, the interstellar medium of a galaxy like the Milky Way is something like 2% heavy elements. And you can think of this in the Milky Way as having those metals 1% in the gas phase and 1% in the solid phase, where solids and dust are the same thing for our purposes. Despite the fact that this sounds like a small amount, as you're going to hear through the whole week, the gas phase metals play an absolutely enormous, both the gas and solid phase metals play an absolutely enormous role in setting the physical state of the interstellar medium. So metals are crucial to cooling the gas across a huge variety of phases. Dust is absolutely essential as a mechanism to shield gas in the interstellar medium and allow it to cool down, but it also serves as a catalyst for interstellar chemistry. There's a really nice compilation here of the breakdown of abundances in the breakdown of abundances in the Milky Way and the Magellanic Clouds for a few key elements, looking at both the overall abundance and the depletion of heavy elements into the solid phase from a very nice review by Frederic. And I referred you to that. So I'm repeating the figure here, but just want to make the point again, as I just pointed out, the absolutely key way that we end up tracing heavy elements and the abundance of heavy elements in other galaxies is by spectroscopy of atomic emission lines from ionized gas. There are other ways to do it. Absorption is crucial to actually trusting all of this, but to give you the simple high-level picture, the thing that we do to map out metallicity variations is to leverage the ratios among optical emission lines, like what you see here, in order to infer the temperature of gas and via this the heavy element abundances. So absorption measurements are crucial, but emission of lines from ionized gas ends up being our workhorse for tracing the distribution of metals. To trace dust, we have a few options. So we can look at the light that is missing, or we can look at the light that is emitted by dust after that light gets reprocessed and re-emitted by dust grains. So both of these essentially just trade on the fact that dust absorbs starlight. And so if we want to measure the structure and amount of dust in galaxies, we either want to infer what starlight should be present and then ask what's missing. And so this means mapping out either extinction or reddening, or we can deploy a more survey-oriented approach by just looking for the emission that reemerges from the dust grains by essentially by conservation of energy. And that involves observing and modeling the infrared spectral energy distribution, which we'll have an entire lecture and we have hands-on projects for. So the emergent infrared spectral energy distribution reflects a combination of how much dust you have, the heating radiation field, the properties of dust, and the dust size distribution. There's a really beautiful figure of this, again, from this review by Galliano et al., illustrating the interplay of observations highlighted here as bands that have had space missions to observe them, and the contributions of different radiation fields, different size populations, and sorts of things. Similar to the hot ionized medium, this is, I will just say for a couple of slides, and then we will not come back to this. But it would be totally remiss to talk about the gas in low redshift galaxies without talking about one of the most active areas of research on this front over the last 10 years. So we talk a lot about the gas in the disk of galaxies, and we will focus on that, I believe, overwhelmingly throughout this conference. But the circumgalactic medium holds an even larger reservoir of gas. And over the last 10 years, there's been an enormous amount of effort on trying to understand the amount and character of this gas around galaxies. This is very challenging because the gas around galaxies in the so-called circumgalactic medium is very low density. It's hot, and that makes it hard to see. So you are thinking about temperatures of 10,000, maybe even of 100,000, maybe even as low as 10,000 in the densest cooled off knots, up to more than 1 million degrees Kelvin in a very massive galaxy or clusters of galaxies. And the Milky Way presumably has a component at this temperature, just going on the hydrostatic equilibrium number. And the key thing here that I really want to emphasize is just that the CGM gas reservoir is potentially very, very big. So this isn't as much mass as the whole ISM disk. This is, the strongest claims about the mass reservoir in the CGM, which have non-trivial associated uncertainties, are that the mass hanging out in the circumgalactic medium of galaxies may have as much mass as the whole galaxy disk itself. The distribution here sprawls out for many tens of kiloparsecs up to several hundred kiloparsecs in a big massive galaxy like the Milky Way. And you might say, who cares? Probably wouldn't say who cares, but because because galaxies fundamentally will run out of gas given cosmic time, the CGM represents an absolutely crucial reservoir of fuel. And because galaxies visibly return material, including metals, but also just gas, from the disk out to the circumgalactic medium, our view of essentially the disk and the circumgalactic medium as a coupled system has become very important to how we understand the ISM and galaxies. And this has been especially true over the last 10 years. So what's been, what's particularly been happening over the last 10 years, and both the figure on the previous slide and the figure on this slide come from a really fantastic review article by Tomlinson et al. From 2017. So over the last decade, there's been enormous progress in absorption measurements targeting the circumgalactic medium, particularly using ultraviolet absorption features. So there's also really important work to be done in the X-ray, but the technology jump came with the ultraviolet spectroscopy with Hubble. And so the problem here is that in order to study this circumgalactic medium in absorption, you need a fortuitously placed background source, or you need to construct your experiment in such a way that it is oriented around background sources. And so people have done a ton of this with the Hubble Space Telescope over the last decade, and we have learned a lot. There's a really beautiful picture here of how the different absorption features running through the ultraviolet and optical, and you can see here that you need space at low Z. So how these different absorption features trace out components at different temperature and density with the grayscale in the background, just giving results from a simulation. To try to sort of put this all together, this is a very rough, terribly incomplete summary figure showing you the sort of mix of phases in the interstellar medium of low redshift galaxies. You can think about H1 and hot gas filling much of the volume, stars forming in the molecular phase, which then will create and power a medium of warm ionized gas. And you can always keep in mind that heavy elements and dust play crucial roles in the heating, shielding, and chemistry of the gas. So the sketch here just totally not proportional or anything like that, but just gives you a clear illustration that we need essentially panchromatic observations in order to access all of the phases of the interstellar medium that make up galaxy disks. I'm not going to read this now, but if you want a mnemonic to summarize the parts of this part of the talk in rhyme, I provided a rhyming summary of part 1 here. And then I've also noted that I've put a couple of notes here on how to think about some of these diagnostics. If we were doing a full-on class, I think these things are worth a lecture, spending a lecture on each, but I don't want to, but essentially this would just eat too much time to go through the details of all of this. So I just put a note or two on the slides here. So I need a minute to take a deep breath as we shift to the next part of the talk. So I'm happy if there are questions right now to ask if there's something urgent, if somebody is keeping an eye on the Slack channel, and if there's something urgent to bring up, I'm happy to clarify or answer a question right now. I'm going to take a sip of coffee, and then we'll move on to the next part.
It depends how many time you'll be there at the end. There are still a lot of questions, so maybe you can take a coffee and we can go back to that after, at the end. How many times did you plan for the question? 15 minutes?
I think the baseline plan is 15 minutes.
Yeah.
And I think this is about the halfway point. So we are roughly about on time.
Okay, so good. So if you need a coffee, just go and take a coffee.
Okay. I will. But feel free to shout if there is something, like if I've said something that is clearly super confusing people, feel free to shout. Okay. So in that case, let's push ahead here. And what I'll talk about next is essentially how much of these phases are present in low redshift galaxies. You've got the sort of level of the overall talk at this point, so I won't give you the calibration speech again, but you can see we're going to be working in very broad brush. I would like you to walk out with a cartoon of how much of different stuff is in roughly different types of galaxies. But as with essentially every single thing I'm saying in this talk, there are like pages or lectures worth of caveats on top of it. But let's start with the atomic gas in galaxies. So I'm going to I will show a slide on early type galaxies at the end of this small set of slides. But right now I'm focusing on galaxies that are actively star forming. And so the crucial thing with the atomic gas, which we've said already, is that, and this is in sharp contrast to what you're going to hear in the lecture later this afternoon or the next lecture, whatever times it is for you at the moment. So is that at redshift 0, atomic gas by roughly a factor of 3 makes up most of the mass in star forming galaxies. If you want to anchor this to the stellar mass for a big galaxy like the Milky Way, maybe 10% of the mass of the baryonic disk is tied up in the ISM, with about half of that in the H1, and the remainder basically split between low density ionized gas and molecular gas. But the fractional ratio of atomic gas to stellar mass is not fixed. It has a very, very clear trend as a function of a galaxy's other properties, with a really beautiful plot of this coming from the gas survey by Catanella et al. Here. And I really refer you to this series of papers for integrated properties of galaxies. It's a really beautiful set of work. So this is plotting the ratio of atomic gas to stellar mass as a function of stellar mass. And what you should see here is there's a very clear, strong trend such that more massive galaxies have lower overall atomic gas content relative to their stellar content. If you think about the Milky Way as hanging out somewhere up here, and then else, in a sort of M star tip of the star forming main sequence galaxy being here-ish, you're looking at kind of 10%-ish type numbers. But if you move down to something that has a mass that is more like a large Magellanic Cloud, or even go over to here towards the small Magellanic Cloud, then you are talking about galaxies that have as much mass in their atomic gas reservoir as they have in their stellar mass. So this is crucial for changing character of the galaxy, and really highlights the fact that, and there are other ways to see this, really highlights the fact that the interstellar medium plays a dominant role as you go to lower and lower and lower mass galaxies. And you could also, I could have shown you a Tully-Fisher and baryonic Tully-Fisher plots to demonstrate that, but I think that this plot is very simple and demonstrates this very nicely. The picture for molecular gas is a little different. So this is from the same series of papers. This is a paper by Saint-Onge et al. From 2017, now plotting, instead of the atomic gas, the molecular gas as a function, again, of stellar mass. And you can see here that there is some trend at the higher masses of declining molecular gas content, but there's an interplay here between star forminess and the H2 content at the high end. So what you really see here is that the molecular gas content remains subdominant at something like 10% of the stellar mass, running all the way through the range of stellar masses that we just looked at. However, cannot emphasize enough that, given what I'm going to show you in the next slide, or in the next few slides, we're going to look at how the heavy element abundance changes as a function of stellar mass. This whole game, this whole game highly depends, so getting a quantitative trend out of this highly depends on your ability to convert from CO emission in order to molecular mass. So the observations here are absolutely fantastic. Our precision knowledge of the metallicity dependence of the CO to H2 conversion factor remains something that can potentially use some work. But this is a really fantastic first order picture of, molecular gas mass remains subdominant relative to the stellar component, even as the H1 mass of galaxies climbs as you go to lower and lower stellar masses. So that's painting a picture where I have some star forming galaxy, I tell you its stellar mass, you know everything. This is absolutely not the case. It really matters, for example, where you find your galaxy, with the classic illustration of this, or the classic example of this being that galaxies that you find in clusters have notable deficiencies in their overall H1 content. Whether or not this deficiency applies to the molecular content has been much more ambiguous, but for almost 30 years, we've known that the galaxies in clusters are deficient relative to similar galaxies in their H1 content. There's a really nice plot of this here from Cortese et al. So this is also a review in which each of these points is a local cluster. And this is showing you the fraction of galaxies that have H1 deficiency greater than a factor of a couple as a function of the mass of the cluster and the temperature inferred from its X-rays. And the point you should internalize here is just being in the environment of a cluster subjects a galaxy to substantial ram pressure effects and can strip away the sprawling extended H1 reservoir, inducing an H1 deficiency. And then you can, if you get interested in this, you can correct the details in this as you get to higher order. Someone should really make a newer version of this plot, but I looked and I could not find one. So the other thing that can, not the cluster plot, the plot I'm showing you over here, this plot. So the other thing that can have an enormous effect on the breakdown of phase and mass in your ISM is, of course, whether you have rammed into another galaxy. And so in the local universe, ULERGs, so very high infrared brightness galaxies, are essentially synonymous with major mergers. Again, not true at high redshift, but true at Z of 0. And these major mergers show their gas become much more compact, much more dense, and more overwhelmingly molecular. So this is being shown here in a plot of the H2 to H1 ratio as a function of the of how IR bright the galaxy is, from a review by Sanders and Mirabella in the 90s. So your mass can tell you whether you expect to be H1 rich or H1 poor relative to the stars, and gives you some expectation for the molecular gas content. Then it also matters whether you're looking at a galaxy that's in a cluster or ramming into another galaxy at the moment. So what about those heavy elements? So the metal content of galaxies also depends very sensitively on the overall mass of the galaxy. And I'll say, so that's expressed as this mass metallicity relation, which is, I'm showing here the compilation from an absolutely voluminous review by Maiolino and Minucci from a couple of years ago that I refer you to if you're at all interested in this topic. So the key thing here is that there's a well-defined relationship between stellar mass and gas phase metallicity. There's also one stellar metallicity, but we're not talking about that here. And this is observed to hold in star-forming galaxies. And that means that a low mass galaxy like the Magellanic Clouds or your favorite dwarf galaxy has lower metallicity than more massive galaxies like the Milky Way. And you can see that these are distilled trends here, and showing you the gas phase metallicity expressed as 12 plus log O over H as a function of M star. And what you see here is that as you move up in stellar mass, your metallicity increases. There's a lot to say about things like saturation and chemical evolution, chemical enrichment models. If you are alarmed by how offset these things are, there are dozens of papers on the fact that it is very difficult to get the exact calibration of the gas phase metal abundance from ionized gas spectroscopy correct. This is a major issue. But I think for purposes of this lecture, just internalize that a little galaxy has a lower heavy element abundance than a more massive galaxy. And there is a well-defined relation between the two, more or less, once you pick your metallicity scale. There is reasonable evidence that this isn't just a mass metallicity relation, although this is not as universally accepted as the existence of the mass metallicity relation. So this is, again, pulled from the same review, but from a paper by Maiolino in 2010. I may be misremembering the reference, but the point here is that this is the mass metallicity relation for galaxies in bins of star formation rate. And the idea would be that there is quite some spread in metallicities at a given stellar mass. And people have looked, and what they see is that the more actively star-forming galaxies tend to have lower metallicity at fixed stellar mass, with the easy story being that this reflects the presence of more pristine gas fueling the star formation. Although many details of this have, there would be a lot more to say here. But you can think of the mass metallicity relationship as appearing likely to have a third parameter. And this is particularly interesting to people attempting to unify a relationship across redshift. Star formation rate is not the only quantity that has been proposed. What about that dust? What about the solids? So when I mentioned dust in the introduction to the phases, we said that essentially in the Milky Way, you could think of the sort of fraction of mass of the metal mass in the solids as being kind of 50%, so that you were sort of one-to-one gas and dust, or sorry, one-to-one heavy elements in gas and heavy elements in dust. This, so if that held, what you would expect is that the dust to gas ratio, which is just expressing the ratio of mass and dust to the overall ratio, to the overall ISM mass, would just track the metallicity. They do correlate, but in more detail, as you go to very low mass galaxies, the dust to gas ratio, at least in many galaxies, appears to drop faster than the gas phase metallicity, implying that the dust to metals ratio, or the fraction of your heavy elements in the solid phase, is dropping as you go to lower and lower mass galaxies. And this is again in a very nice compilation from Galliano et al., heavily leveraging work by Remy Rouillet and Suzanne Madden's group. And so the thing you would internalize here is that there is good evidence, which we'll hear a ton more about later in this week, that as you go to very low metallicity, and that implies going to low stellar mass galaxies, so as you go to dwarf galaxies, there's evidence that the fraction of the heavy elements depleted into the solid phase diminishes. And there are reasonable explanations for this in terms of both simple and more complex evolutionary models for dust. And I think we will hear about them in lectures later this week. I kind of give you a picture here that should give you a first order picture. If you wanted to think about star forming galaxies, you can, I can tell you the stellar mass and say, I got a little galaxy. I expect it to have a lot of H1 relative to the stars, maybe about the same H2. It's got lower metallicity. If it's very little, maybe it's not keeping so many of those metals in the solid phase. What about early types? There's, in the field, 30% of galaxies are low specific star formation rate, more red and dead, and there's reasons to not use all of these terms, galaxies. And in clusters, this number climbs even higher. So early type galaxies, the view that they are totally red and dead persisted for a long time. There's been quite a bit of work over the last 20 years to show that it is, in fact, quite common that if you stare at an early type galaxy, you can detect the presence of CO, H1 emission, indicating that maybe something like 30% of early type galaxies have detectable interstellar gas. There's been really nice work on this by Francois Combs and Lisa Young. But in a really nice stacking exercise, again, from this series of gas papers, there's a nice illustration here of the fact that, the fractional contribution of the interstellar medium in these early type galaxies, even when there is an ISM present, it's usually pretty small. And you can see that here in terms of expressing the FH2, so the H2 to stellar mass ratio for galaxies that are at low star formation rate. So let me, so if you were at low star formation rate for your stellar mass, you're down here. And you can see that you have quite a small percent of your overall mass held in the interstellar medium, even when you have a detectable interstellar medium. So I sort of just said all of these things in giving the sketch, but a good first order sketch would be that the gas fraction of galaxies depends on stellar mass. High mass galaxies have more stellar mass relative to gas mass. Little galaxies have more of their overall baryonic material in the gas phase. Molecular gas fraction of galaxies does depend on stellar mass, but it kind of flattens out over a lot of the dynamic range. Metallicity scales with stellar mass and star formation rate. with the dust to gas ratio tracking metallicity, but then for very low mass galaxies dropping such that for the lowest mass galaxies, your dust to metals ratio is very low. And then you can have quite a bit of influence of either interactions directly with another galaxy or being in a cluster. Again, we won't do this right now, but if you want to summarize the second part of the talk here in a rhyme, I've provided you with a rhyming summary of part 2. So I would then shift to the third and sort of final part of the talk to discuss the structure of the ISM and galaxies. Has anyone pointed out an absolutely burning question, or?
No, there are a lot of them, so I will keep them for the end. But you will have some work in the Slack for sure. Okay,
sounds good. All right, so I'm gonna then say that the last bit of the talk here that is going to focus on how the ISM is structured inside these low redshift galaxies. And I've listed these as separate topics here, but I'm really going to just present together the structure of the ISM and Z=0 galaxies, and then say a word about the rate of star formation relative to the gas supply. So first, let's talk about the sort of radial distribution of these different gas phases. So this is illustrated for one galaxy here. But the general trend has been shown to hold in studies of more than 100 galaxies. And so the different phases of the ISM are distributed in different ways. That's your sort of first order important thing to take away. So if you were thinking about a late type, meaning actively star forming disk galaxy, the thing that you can think about is basically that the molecular gas follows as the stellar disk. So you can see that here, this is a plot of the mass per unit area. This is the molecular gas phase. This is the surface density of stars, of stellar mass. So you can see the molecular gas tracking the stellar mass with this offset that we just saw in the previous part of the talk in overall normalization. So these things track one another. If you had put a plot of the distribution of star formation activity, it would also look quite similar. So there are important second order details, but to first order, you can imagine that you would see in a very late type pure disk galaxy that you just see exponential decay in the molecular gas, atomic gas, or in the molecular gas, stellar disk, and star formation activity. But by contrast, the atomic gas disk shows a much more extended distribution with a much narrower range of surface densities than the other phases, right? So this is the profile of atomic gas mass per unit area. And if you look at this and you look at these things, you'd say one of these things is not like the others. And what you see here is some evidence for a bit of a depression in the center as the gas becomes molecular. Quite a narrow range here of mass per unit area for the H1, and then it does decay as you get out here. But the atomic gas has become the dominant part of the disk by mass as you move out. Before that happens, and then the decay is longer and slower than it is for the other components. For reference here, these dashed lines are showing you, this is showing you the classical definition of the optical radius for local galaxies. This is R25. This is giving the same text, but just visually showing what we're saying, which is just that while the molecular gas, stars, and star formation are concentrated to the inner parts and then show an exponential decay, you can see visually in a classic picture here on looking at the galaxies NGC 1646, that the H1 on the same spatial scale just sprawls outward and shows substantially less internal structure. This is a good first order picture. As soon as you put a bulge or stellar bar in the galaxy, it's got a good chance of breaking. So I'm illustrating the effect of stellar bars here. For bulges, often what you will see is that the bulge or spheroidal component of the galaxy is essentially gas-free. Stellar bars do something very interesting, which is, and you can see an illustration of this for one of the sort of Fang-Zolma targets over here on the left. A stellar bar is a mode excited in the disk. It looks like a linear feature when you're looking at maps that trace the stellar mass of galaxies. Something like 2/3 of present-day galaxies have them at some strength. But the thing that they do to the ISM is that they, sorry, the dog came in. The thing that they do to the ISM is they funnel gas from the outer part of the galaxy to the galaxy center. So you can see this very dramatically demonstrated here, as these linear features represent flows along the stellar bar from the outer part of this galaxy to the center part of this galaxy. And the red here is showing you the glow of CO emissions. So you're watching molecular gas channeled to the center of the galaxy. So this gives a mechanism by which stellar bars create enhancements in the gas distribution at the centers of galaxies. You can see a version of this illustrated here on the right. This is another one of these plots that shows as a function of galactocentric radius, the distribution of different components. And you can see here that in this galaxy, there's a spike in the overall mass and star formation activity at the center of the galaxy. So stellar bars are capable of funneling gas to galaxy centers and creating gas concentrations of star formation activity that lead to nuclear starbursts, or what are sometimes called central molecular zones. The CMZ, of course, is a feature in our own Milky Way galaxy, and it's created by this kind of action by the stellar bar, originally recognized from things like COBE in our own galaxy. So stellar bars are a really powerful way to create starbursts without major mergers internal to normal. This is your secular way to create starbursts in local galaxies. So this is giving you, we sketched the radial distribution here. So what if we turn the galaxy on its side and ask what's the vertical distribution of gas looks like? So what does the vertical distribution of gas look like? I'm illustrating this in two plots here. One pulled from a really nice review of the Milky Way, of the H1 distribution in the Milky Way. And the other one here pulled from a series of papers by Keizhong Yim et al., who did a really extensive series of studies trying to use the karma array to study edge-on distributions of molecular gas in galaxies. And I think this is the best set of studies of the edge-on ISM in galaxies. It's a really nice piece of work. And so what you can see here is that for the atomic gas, in the inner parts of galaxies, say out to around the solar circle, you are looking at scale heights of maybe a few hundred parsecs. But that what very clearly happens as a function of radius is that the thickness of the gas layer, which is what's being plotted in both of these, increases as you move out. So this is, understood to reflect the fact that the gas in galaxy disks is sitting in some kind of dynamical equilibrium with the potential well of the galaxy, and that in the outer part of galaxies, this H1 layer increases in height, flaring, in response to the diminished potential well, particularly as the stellar disk diminishes in its overall gravity. So the H1 disk flares, and we believe that this reflects the potential well becomes shallower and shallower as you move out in the disk. What about the molecular gas? Well, it's hard to get quite so far out simply because you need to be able to see the stuff. So I'm showing a similar plot here, but now shifting to the review, again, very nice by Heyer and Dame, of the molecular gas in the Milky Way. And what you can see here is that the thickness, so this is the full width half max thickness of the molecular gas layer for the Milky Way in CO is about 100 parsecs. And you can see from the same Yim et al. Study that this is not a terrible, order this number is not a terrible thing to think about as describing edge-on distributions in nearby galaxies. There is some evidence here that there is a similar flaring as you move further and further out, but you are frankly running out of signal and the ability to do this kind of analysis as you move out because, as we had said, and I won't jump around much, but, as you've moved out, the overall amount of molecular gas is diminished substantially. Well, you have plenty of H1 to work with. So this is our sort of reasonable, that's our distributions of molecular and atomic gas. Radially and vertically. What about the distribution of those heavy elements? So the heavy elements also change as you move around in a galaxy. So this is a plot taken from, this is a plot again taken from the review by Maiolini and Minucci, but they are reproducing a plot from Belfiore et al. which is this absolutely beautiful analysis of metallicity gradients in the manga galaxies. And what you're looking at here is metallicity within galaxies at fixed bins of stellar mass. So this is M star. And you're looking at how this changes as a function of radius expressed in terms of the half mass radius. And what you should see is that the metallicity goes down. And so the galaxies display a characteristic metallicity gradient such that they have less heavy elements relative to their ISM as you move from the inside to the outside of a galaxy. And if you're expressing things in terms of the sort of R25, which I'm not saying that we should be using R25, that's the way local galaxies worked in the past. You could think about a typical gradient as sort of 0.2 or 0.3 dex over the full optical radius of the galaxy. There are many versions of these metallicity gradients, including some suggestions that, if you correctly normalize everything, there are some approximately universal gradients, but then also demonstrations, things like galaxy size or a host of other things can act as third parameters. So I think the important thing to be carrying around is that a typical galaxy, a typical star-forming galaxy will display a metallicity gradient in addition to having a metallicity set by its overall mass. So this gives us overall radial structure of, and I will not show a slide on it. The other point to make, of course, would be that, as the metallicity drops, the dust abundance will also become lower and lower. And there is anecdotal, but not this kind of synthetic evidence that the dust to metals ratio will also drop dramatically as you move out in a disk, meaning that dust becomes scarcer even faster than the metals become scarce. So that gives you the sort of sketch of the kind of radial and vertical behavior of the ISM components. The last bit of structure that I wanted to show you was just to emphasize that, that molecular gas layer, which is showing up as, it's got some full width half max, it's got some radial distribution. That might give you the impression that it's smooth. It's not. Nothing could be further from the truth. The molecular gas traced by CO, or whatever your favorite tracer is heavily clumped up into molecular clouds. So these are dense, roughly gravitationally bound collections of material that essentially act as stellar nurseries in most galaxies. And so the key thing here is that when you observe a galaxy in molecular gas at high enough resolution, it's going to resolve into these individual features. And so you can see an example of this with one of the CO maps from the Fangsalma survey here, where you've resolved this nearby galaxy such that these little individual clumps now have scale that is comparable to the full Orion cloud complex, right? So you're seeing this resolve into individual clumped up features. I'd gone over these numbers when we originally talked about the molecular ISM, but I just want to emphasize again, as you heavily resolve a galaxy in molecular gas, what you see is that the gas resolves into a structured medium with the individual clumps, not always perfectly well defined, but having characteristic sizes of order tens to hundreds of parsecs, masses 10 to the 4, 10 to the 5th, up through a few times 10 to the 7. What is very clear is that the motions are not thermal in origin, but are believed to be dominated by turbulence, although other sources of motion may play an important role. And you can see that at all scales, the structure appears clumpy and filamentary, and you'll hear a lot more about this at smaller scales as we move forward in the week. So I'm not going to give a full Larson scaling relations description here, mostly because I actually think that this is probably because I actually think that this is the constructive way to talk about these things in other galaxies going forward. So I'm probably be more interpretive here than anywhere else. But so I think that either the line width or, as you'll commonly see, looking at the line width or the quantity sigma squared over R as a function of surface density has become a key way to diagnose the physical state of molecular clouds in galaxies. And the reason for this is just that, so this is a simplified version of using just the line width, but the reason for this is that if you can measure the line width at a fixed size scale, there's a basic expectation for how the surface density relates to this line width normalized by size, given some dynamical state for the cloud. And so dynamical state is just a fancy way of saying if a cloud is virialized, you expect a line that looks like this. If a cloud is marginally bound, meaning the potential energy equals the kinetic energy, it looks something like this, and so on. So a plot like this then gives us a way to simultaneously look at how the mass surface density of molecular gas is varying at high resolution, and how the dynamical state of that gas is looking at high resolution. And because the turbulent pressure goes as rho sigma squared, it's also the case that as you move from the lower left to the top right of this plot, you're watching changes in the turbulent pressure of the molecular medium. So with all that said, this is a plot of where essentially each dot is one GMC. It's 100,000 giant molecular clouds in the Fangs-Alma galaxies, which is a main piece of work coming out of GISM's thesis. So there's a presentation of this in papers from 2020 and 2018, and a really nice complementary view decomposing the emission in Rozlowski et al. 2021. And what you see here is that at 100-ish parsec resolution, I think that this one is 150, but there are versions of the plots at 120 and 90. You can see that the gas mass surface density at high resolution varies in galaxies, and that the line width varies in a way that correlates with this, so that it appears that the molecular gas in galaxies hovers near the gravitationally bound state. It's very hard to put an exact prefactor on this because you need to know the detailed subgrid density distribution. But you can think about gas as living as being nearly gravitationally self-bound. And you can think of the gas mass surface density as varying along with the line width of molecular clouds, reflecting that the internal pressure of molecular clouds is a pretty strong function of where you look across the local galaxy population. If you've been following along, it shouldn't come as any shock to say that, if you plot the locations of gas that's been heavily influenced and driven to the center of galaxies by stellar bars, it shows up in a different part of this diagram than the gas in disks. And that's exactly what's going on up here. These high line width, high surface density points are places where molecular gas has been funneled to the center of galaxies by stellar bars and driven to have very, very strong motions and perhaps pushed a little bit out of gravitational equilibrium and into a more diffuse component where it's being bound not by self-gravity, but by the potential well of the stars. So the last point I would make, so I think that these plots that look at variation of surface density and line width, or mass and line width, and look at how pressure, dynamical state vary are really constructive ways to move forward in this field. I think it's also worth pointing out sort of how the mass function of these molecular clouds works. So when you decompose a galaxy, a nearby galaxy into molecular clouds, you can construct a mass spectrum. There's a really nice summary of this in a review by Fukui and Kawamura, building on work by Rozlowski in 2005. And the sense of this is that similar to the Milky Way, a reasonable characteristic number to be thinking about for the slope of mass functions in molecular clouds in nearby galaxies is something like -1.5. So mass function slopes are something that does have a magic number. So when expressed in this sort of dn/dm way, you're talking about equal power per decade of mass if you're at -2. So this instead means that molecular clouds tend to hold more of the mass and more of the star formation activity in the most massive elements of the population. Although, again, there are caveats on all of this, and there are some cases with slopes observed to be steeper. You can see an example at this time that M33 was behaving differently. In particular, the parts of M33 were behaving differently. So the last few words I'm going to say here are on how star formation fits into this overall picture. And I'm just going to make 3 quick points here on the overall rate on the sort of phase correlation of star formation, the overall rate of star formation, and then what happens if you observe star formation at super high resolution. So the first point is on just the phase correlation. So you know, for people who study the Milky Way, it's probably not a shock to say that as we have gotten more and more maps of nearby galaxies in molecular gas, and more maps of where star formation is occurring in nearby galaxies, star formation activity is occurring in nearby galaxies. What we have consistently seen is that the location of star formation and the rate of star formation internal to a galaxy correlates more cleanly with the location of molecular gas than it does with the location of atomic gas. This is still, I think, one of the nicest plots of this from a part of thesis work by Andreas Schruba in 2011, just showing you for regions inside a set of 30 galaxies, how the molecular gas per unit area on the right correlates with the star formation rate per unit area. You can see that this is, while not perfectly one-to-one, there are important galaxy-to-galaxy variations, and centers do some different stuff. You know, overall, there's a pretty clean, straightforward correlation between these phases. By contrast, if you look at the correlation between the H1 and the star formation activity per unit area, what you see is a very weak relationship in the interior parts of galaxies. So this is just the zoomed out version of saying we watch stars forming in molecular clouds in the Milky Way and the nearest galaxies. And that's, as far as we can tell, stars form in molecular gas. There's a detailed physical point to be made about whether the formation of molecular gas is causal or coincidental. And I think that, you know, there is a reasonable argument to be made that the conditions that lead to star formation have to lead H1 to convert to H2. So this may be a thing that happens at the same time. But either way, dense Will-shielded gas tends to be molecular, and molecular gas appears to be where the stars form. Across both low and high redshift, one of the sort of characteristic numbers that you will hear discussed is the molecular gas depletion time. So this is formally just taking the mass of gas, in this case molecular gas, but this is also phrased in terms of H1 or total gas. This is taking the mass of molecular gas and dividing it by the star formation rate. So you're asking how long would it take the present day rate of star formation to chew through the available gas reservoir. So this is a consumption time or a depletion time. In reality, we don't actually expect such a passive evolution. So physically, you can think of this as being a measure of the star formation rate per unit gas mass, just upside down. So this is, you know, I think that the physical meaning here is a specific rate of star formation specific to the gas mass, but expressed upside down so that you can quote it in years. So the molecular gas depletion time is of order a gigayear, but is observed to correlate with the specific star formation rate, and it may depend on stellar mass, with that same caveat, which I'll emphasize again in just a sec. So again, these are some very nice plots from the gas survey here from St. Angedal 2017. And what you can see is that there's an apparent correlation between the depletion time of molecular gas and the stellar mass, and a very strong, albeit correlated axes, anti-correlation between the depletion time of molecular gas and the specific star formation rate, such that galaxies that have a higher star formation rate relative to their stellar mass also have a higher star formation rate relative to their gas mass. So the details, especially of this relationship here, depend, again, very sensitively on how you treat the CO to H2 conversion factor, because remember that this stellar mass here also drives changes in metallicity, and that we expect the CO to H2 conversion factor to change as a function of metallicity. So there are, for example, just to highlight, there's a really beautiful review by Tacconi et al. From last year, which I believe makes the argument that the stellar mass, the depletion time versus stellar mass trend is not significant. And as near as I can tell, this is largely down to how the conversion factor is treated as a function of stellar mass. So if you really want to understand this trend, oops, figure out alpha CO. So the last point that I'll make here, and then I guess I'm talking a little fast and we didn't stop for questions, so that'll give us plenty of time for questions, is just that, you know, so this is giving you a sketch of where in a galaxy the star formation occurs. So it occurs coincident with the molecular gas. It's giving you a sketch of how fast star formation occurs relative to the gas supply. It occurs faster for more nearly starburst galaxies, and it occurs apparently faster for low mass galaxies, slower for high mass galaxies or more quiescent galaxies. But of course, and there's a whole project on this in M33, as you move to very high resolution, talking about star formation rates and integrated gas masses stops capturing any of the nuance of the star formation cycle. And so a major place where there's been a lot of activity, I would say spurred by a couple of studies here over the last 10 years, has been in investigating what happens as you resolve the star forming process. And so the idea here is that in fact, star formation in any given region is going to occur over a cycle of cloud formation, star formation feedback, and cloud destruction, with characteristic timescales solved for here of something like 20 mega years. And what that means is that if you zoom in on any individual star forming region in any galaxy, what you're going to see is a star forming region in some evolutionary state. So Kawamura et al., as part of the Nanten series of papers that laid a lot of the groundwork for this field, does this by identifying individual GMCs as having no star formation, having an associated H2 region, having a visible cluster, or as clusters that have already dispersed their molecular clouds, and then attempts to use population statistics. Another way to look at this is simply to say that as you move to higher and higher resolution, there's not a depletion time for a system, but that the ratio of star formation activity to gas mass in different phases will depend on what type of peak you are looking at. Am I looking at an H2 region, in which case I may have already dispersed my molecular gas, or am I looking at a molecular cloud, in which case stars may not have started forming yet? And so this is nicely illustrated in this, again, as part of Andreas Schruba's thesis, this tuning fork style diagram that's had really beautiful work done on it by Melanie Chavance and her collaborators over the last few years. So to summarize the sort of sketch for this section, what you should be carrying around is that molecular gas, stars, and star formation activity roughly fall off as an exponential disk in galaxies. This situation is perturbed by the presence of bulges and stellar bars, especially because bars funnel gas to galaxy centers, which create concentrations of gas and star formation. So in the inner disk, both molecular and atomic gas appear to be lying in a relatively thin layer. If we had done stuff on the diffuse ionized gas, that would appear to be a bit thicker, but hard to figure out because of the lack of a linear tracer of mass. As you move out in radius, H1 shows evidence of flaring, increasing its overall scale height in both the Milky Way and other galaxies. Just as the gas surface density is dropping, the metallicity, so the metal content per unit gas of galaxies, also drops as a function of radius, with a reasonable number being sort of 0.2 to 0.3 dex across the full optical radius. Dust shows similar or even steeper trends. The molecular gas is not smooth, but clumped up into giant molecular clouds. These things are dense, they're turbulent, and they hover around being bound by self-gravity. Their properties do vary across the galaxy population, and the sense of, one of the senses of this is that there's more turbulent and less bound gas in starburst and galaxy centers. Star formation tracks the molecular gas, with depletion time variations observed as a function of stellar mass and star formation rate, but dependent on our knowledge of the CO to H2 conversion factor. And then at high enough resolution, the active cycle of cloud formation, star formation, and feedback, as well as cloud destruction, becomes visible in high resolution observations. So then, to help you remember this is a rhyming summary of the third part of the talk. Since we are not pausing for individual part questions, that brings me to the conclusion of the talk. I'm going to try to read, I considered saying that we had all agreed to do rhyming summaries of our talks, but that seemed unfair to the rest of the SSE. So I'm going to try to read the rhyming summary here. We'll see how this goes. And say, the spin flip line reveals atomic gas, which fills the space and holds a lot of mass. New stars are born in clouds we can't directly see, We get around this by observing states of C. Warm bubbles of dense gas encase each massive star, but their ionizing light still makes it pretty far. The light from these young stars runs headlong into dust. To trace these grains, IR emission is a must. When massive stars explode, they blast the gas away and shock what's left to upwards of 1 million K. Last, while this disk of gas can let the system grow, it's still not much compared to the halo. At Z of naught, H1's the bulk of gas by far. A little dwarf can even have more gas than stars. Fractionally, the H2 remains quite low, though in detail this depends on XCO. Clusters strip gas and major mergers make it dense. And early types have gas, but just a few percents. The metal content follows from the system's weight, with little dwarfs at metallicities of 8. Solids, the dustiness tracks metallicity, but with a steep dependence, leaving dwarfs dust-free. As an exponential disk, both CO and starlight fall, while H1 at nearly fixed NH just sprawls. A stellar bar can cause a deviation from this scheme, since gas inflow can make the center quite extreme. Now, the cold gas in the inner disk, it lies in a thin layer, but at large R, with fewer stars, the H1 disk does flare. Increasing radius, it also drops the metal count, which may go down by 0.3 dex before the stars run out. That H2 gas, of course, it's clumped in GMCs. Cold, dense clouds that play the role of stellar nurseries. The speed with which that cold, dense gas supply gets ate, it varies with the mass and star formation rate. So that's my low Z ISM collection. Now to you, I ask for questions and corrections.
Thanks a lot, Adam.
Sure, no problem.
I'm very happy to have this record on also the slide, because I need to read that again. It's very nice. Thank you. So as I said, there are plenty of questions, so I've tried to order them by different theme and take few of them, just maybe representative or not, but you will have plenty of time to answer all of them in the Slack. So on the warm ionized medium, there is a question about the relation between, to calibrate the mass of the warm ionized gas. Is there any relation, in fact, to calibrate the mass of the warm?
So this is, and I absolutely invite answers from the other panelists on this. I mean, so what I would say is that this is very hard. And so one of the blanked out slide that I sort of blew past emphasized the difference between emission measure and column density, right? And so the trouble with the diffuse ionized gas or warm ionized medium is that the best way to see it is to look at faint H alpha emission. But of course, H alpha depends on n squared, so the integral n squared dl, which leaves you in a regime where you need to know n in order to interpret your brightness as a mass tracer. So you can come to the Milky Way where you can get lucky and use, you know, an O, B star or something as a background source to try to work this out. And because of that, I would say that the 20 or 30% that I'm kicking around is mostly influenced by the WAM studies by Hafner and folks like that. But I think that, and again, I would absolutely love it if one of the other panelists has a better answer to this. But to my knowledge, no, we do not have a straightforward tracer of the mass of the WIM or DIG in other galaxies. We have tracers of its presence, but we lack a straightforward linear tracer of its mass, and that's a big problem for getting the exact bookkeeping right.
Okay, and on the same line, with H1, how do you use H1 to measure the mass?
So this one I can be much more cheerful about. You could do this in a couple of different ways, but look, to first order, the temperature difference between the two states is 0 essentially. So, and the Einstein A coefficient means that it takes forever to decay. So you can essentially just trust that if you find a cloud of atomic gas in the disk of a galaxy, it's less clear you can do this in CGM, that the collisions have populated the upper and lower state of the hyperfine transition according to the degeneracies, which are 3 to 1. And then, you know, you can think of this as just measuring oh, when I capture a 21 centimeter photon, if I'm assuming optically thin, then I know that something sat in the upper state, and I know the Einstein A that tells me how long it takes that thing to decay. And I can just multiply those numbers and say, I know that there were this many things hanging out in the upper state there, and I know how many, the correction factor, in order to account for the level populations of the two states, because it's trivial for H1, and then you can essentially just put a number in front of it. That breaks, and the Milky Way people are wincing, of course, when optical depth becomes a concern. And if you're looking at an edge-on galaxy, the 21 centimeter line can become optically thick, and then you just need to, then you need to account for the optical depth effects. But if you're looking down at a face, if you're looking at a face-on galaxy, then this is not an overwhelming concern. And there are some really nice synthetic studies suggesting that the integrated effect of optical depth on the 21 centimeter line has an effect of maybe 20 or 30%.
Okay, thank you. Then on the CO, how come CO is the second most abundant molecule in molecular gas? How do you know that? And why not other one?
There's a lot of carbon and oxygen. And there's a straightforward path to make the thing. So there are not a ton of there's not two equally competing species that drop out of gas phase chemistry. So you have your most abundant, you have your most abundant elements, and you have a straightforward path to make it. And you get enough dust shielding to keep the thing from being dissociated, or even build up some self-shielding. I think that there's, if someone has a deeper why than that, I'm open to it, but I think that's basically, stars made a lot of CNO, and then nature provided a pathway to make the stuff and protect it, and did not create a competitor.
Okay, so again on the CO, so it's understood why the CO is varying with the metallic content, but why does the CO light to mass ratio conversion factor vary also with metallic content?
Yeah, so there's a bit to say here. So first, definitions of alpha CO can vary according to scale, and this can get us in a lot of trouble when we try to talk between the Milky Way and other communities. So in the extragalactic sense, molecular gas that is locally free or very poor in CO, but is still H2, is swept into that conversion factor. So first, on the metallicity term, that number should get higher in order to account, say, if I have, a factor of 10 more gas hanging out without any CO associated with it, we would up the alpha CO by a factor of 10 to account for that. And you can see that this is essentially what you have to do when you are studying integrated galaxies if you want a conversion between the CO luminosity of a galaxy and the total molecular mass. But that's towards the metallicity side, right? It's also worth making just a brief statement. I think that we'll come back to this later in the week with discussions of PDRs and things like that. But that, in fact, a little bit paradoxically, it's actually the low metallicity driving the low dust abundance as much as it is the absence of CNO that leads to this relatively low CO abundance gas, because with poorer shielding, the molecules that can dissociate CO, the photons that can dissociate CO hammer into the cloud and get further into it. As far as the excitation stuff, so the point here would just be that the emissivity, so the light per column, is essentially what's setting the conversion factor for parts of a cloud that do have CO. And so, like, the simplest way to see this is that CO is usually about optically thick. So the source function of the gas should make a difference, right? If I turn up the source function from a 10 Kelvin black body to a 50 Kelvin black body, then, if we're on the Rayleigh-Jeans tail, I get a commensurate increase of 5 in the amount of light I get per unit mass, right? Just because the temperature makes the gas more emissive. So this gets more complicated as you attempt to say, if I make the gas more optically thin, then it will get better at emitting. So a tau of 2 gas is better at emitting than a tau of 20 gas because you just see the surface of the thing, right? So I think the one sentence version of this, without getting totally bogged down here, is just that the details of radiative transfer and excitation matter to how much light you produce per unit mass of the CO. And that's what drives the excitation, or what's often referred to as the starburst part of the conversion factor.
Okay, thank you. If you want to answer that in the Slack, it will be very long answer. You have to type for a lot of time. Yeah. Other question about the SFR and metallicity. What explanation have been suggested for the stellar mass metallicity relation, and does the active star formation rate affect the initial mass function? And how does this translate for the high redshift galaxy, especially the high dusty star forming galaxies at high redshift, because the metallicity cannot be very high in the very early universe?
Okay, so there's a whole lot of questions there.
Yes.
I'm not.
You have 5 minutes left.
Okay, so I am hardly the expert on all of these things, but I will say a few things. So first, remember that when you see bright systems at high redshift, you tend to be picking out the highest mass halos. And so if you go look even at high redshift quasars sitting in the deepest parts of the most massive halos, the metallicity can be surprisingly high. It's not impossible to get that half solar or even higher in. And so when you look at the absolute highest mass things at high redshift, you don't want to assume a characteristic metallicity for a redshift. Then working backwards, the reason that people have attempted to propose these third parameter, or a reason that people have attempted to propose these sort of third parameters to the mass metallicity relationship has partially been to unify relationships across redshift. The Maiolino and Minucci review has some beautiful plots of this. But the mass metallicity relation does evolve as a function of redshift, so that at a fixed stellar mass, as you go to higher redshift, you see lower metallicity. And so attempting to get a unified picture, of these things has been one of the reasons, where one relation applies across redshift, because it's accurately reflecting the overall underlying physics, has been a goal. Then in terms of the heavy element abundance, in terms of some kind of model for these things, there are absolutely well-developed models of galaxy enrichment. I may misquote the reference here, but I think there's some nice papers by Zahid, for example, where and it's not in spirit terribly dissimilar to some of the models for dust evolution and growth that Frederic has worked out along with others for dust. But essentially you are looking at star formation, providing back some metals. So you start with an unenriched system, you get some yield, you also send some stuff back to the circumgalactic medium, and then you can run evolutionary tracks in an attempt to match this up, treating the accretion, the return, and the yield as open parameters. And these things, people have used the mass metallicity relation exactly as a constraint on these things to try to understand the physics of galaxy formation using the metals as a tracer of overall evolution. That was too long, but.
Okay, thank you. Maybe a last one. There is a question about Bacchini et al. That have shown that the H1 volume density correlates very well with star formation, which is not the case for the H1 surface density. So do you have any thought about this? How can that be?
I think that there may be a point of confusion, because column density and surface density should be the same within a few, within a unit's change. And
but it's speaking about volume density.
Oh, volume density.
Yes.
Sure.
There is a correlation, between volume density and star formation.
Absolutely. No, for sure. So I think that this relates back to the vertical structure stuff that I was showing with the flaring of the H1 disk in the outer parts, right? So a very easy answer to this is just that you can get quite high column density in the outer parts of galaxies when that vertical distribution flares out to have thickness of a kiloparsec. And of course, that puts a lot of material at low densities, which is not at all ready to be knocked by a gravitational perturbation or anything else into a dense star-forming cloud. So this absolutely makes sense and fits in with an overall picture where the volume density, or that vertical distribution, which is heavily influenced by the stellar potential well, plays a critical role in setting the ability of the atomic gas to knock over into a denser phase and form stars. So I think the way to think about this is just the path length is the translation between volume density and surface density. And for sure, when you have a smaller path length, you have a bunch of denser material, which is much more ready to form stars. I think that's absolutely.
Okay, thank you. And then the most popular question by far was about your dog. What is his name?
The dog's name is Bella.
Okay, thank you.
Sure.
He's around, or they want to show?
She ran upstairs.
Okay. Okay, thank you so much. So I think it's time for a break, a small break, before having the next lecture.